Okay. So yeah, hello guys. So I'm Jishnu and I'm joined by Shobit and we'll be talking about SinGAN. So it is basically a version of GAN which uses a single natural image to learn generative model for generating natural images. Oh, Shobit, can you go to the next slide? Yeah, so this would be the outline for our presentation. First, we'll go over the GANs, like what GANs generally do, and then we'll probably go towards this ecosystem of GANs, like what are they doing, what are the internal entities associated with GANs, and similar stuff. And then we'll start explaining about GANs, the architecture, the experiments that these guys have done, and also we'll show some of the results that are really cool towards the end. Okay, next. So, so right now when we are reading the literature, we came to know this classical GANs, right? So we have just given this name classical because we wanted to uh, give a clear distinction between SinGAN and the other GANs because oh, can you go back? So classical.
Jishnu, can you be a little louder, please?
Is this fine? This voice?
Yeah.
Okay.
Thanks.
Okay. So these classical GANs are basically the term coined by us for this presentation. So the thing is, classical GANs basically require a lot of image data to learn the probability distribution. So what GANs essentially do is they eat up a lot of data, let's say images, and what they try to do is they basically try to learn the probability distribution of those images, and they try to encode it in some way. Now, when this encoding is done, we can use this encoding to generate many more images similar to the images that were given to the generator. But the cool thing about this is like the images that would be generated, right? Those images would be nearly looking similar to the natural images with some changes that you can obviously see. But it would be really difficult for a human to differentiate between those images. It's like as a human, we won't. Oh. Is this, I'm audible, right? Hello?
Yes.
Oh, yeah. So as a human, it would be difficult for us also to differentiate between those two images. Now, the problem with classical GANs is like they require a lot of data. It's like you have to have a image data set. And again, when you do a lot of effort and you create this image data set, you feed into these GANs. Now, when these GANs learn this probability distribution,
Vishnu,
Yeah.
I think that there is some problem with your microphone because when we say we can't hear you, I mean, for a moment it's clear, and then the next second it is again very can't hear you at all.
okay, am I audible now?
Not really.
Okay, now?
No, you have to be a little bit louder.
I think there is some problem with the microphone. Okay. How to manage this? Hello, am I audible?
A little bit better than before, but try to be more clearer.
Right now,
Yeah,
fine,
can
right?
continue.
Okay. So should I start from the beginning or like? Hello. Hello.
Yeah. Yes. Hello.
Okay. Generally the GANs, classical GANs basically require a lot of data set. We'll put a lot of effort and we'll generate the data set and then we'll feed into the GANs. Now, again, there would be a problem from the output point of view because the data that it would generate, right? So that would be data set specific in the sense it would learn the distribution of the data set and it would try to generate the images similar to the data set. So it is quite, it's not a good thing because we cannot feed in like the all the images that we want to generate, right? It can be like, let's say we give a sports data set to the GAN and it will generate sports related things. But what about this natural images? So that was a problem. Now again, that is the third problem. Let's say it's application specific because a lot of these GANs actually tackle this problem of either super resolution or texture synthesis or something of that sort. So GANs basically tackle a specific application and then they try to improve the accuracy or quality of the image that are being generated. So application specific results are also downsized for classical GANs. So most of these GANs face the above mentioned problems of large image dataset requirement, dataset specific results, and application specific implementations. Now this is where SinGAN comes to the rescue, because it is not dependent on anything. So let's say if you feed it image of an animal, it would try to learn the probability distribution, and it may come up with something else. So we'll show some examples towards the end of this presentation. At that point, it would be more clear. So it's like you give it a random image, it will generate random samples via observing this patch distribution. So this patch distribution is the key for SinGANs. We'll discuss this more when we'll talk about the architecture of SinGANs. Now, the cool thing about this SinGAN is like results are not application specific or data specific. So it's a huge relief for this computer vision community, because like we won't be needing to create a data set, and like we won't have to deal with specific applications. Like once you train SinGAN, you can use it for many image manipulation tasks. So it is useful in a wide range of applications. So this is basically the premise of what this SinGAN's authors wanted to achieve while they were doing this research, right? And yeah, next slide.
Yes, so before we go to the SinGAN architecture, let's discuss a little bit about the classic GAN structure. So in classic GANs, we have a discriminator network here and a generator network. Now what generator tries to do is it tries to sample some images given some noise vector. Okay. Now discriminator's job is to discriminate or tell the difference between the real images and the generator's generated images. So it's like a min-max game where discriminator tries to uh, distinguish between these two images, and generator's job is to synthesize realistic images so that discriminator cannot discriminate between the two. So that's basically like a game. So the GAN ecosystem, it basically requires a lot of training data for this purpose. And there is a single generator. It generates images similar to the original distribution, and discriminator tries to discriminate between real and fake images or the generated images. And this is the adversarial loss, or the loss which is used in the GAN architecture, where you can see the discriminator is trying to mm, increase the loss, and generator is trying to minimize it. uh, it is more about the adversarial loss. So here we can see dx is the estimate probability of that the image is real, and ex is the expected overall value for real data. uh, gz is the generator's output when given noise z, and d dgz is discriminator's estimate of probability that it is a fake. So for generator, a generator has control over only this quantity. So it will try to reduce the probability distribution that discriminator will think it is a fake image. Like it has to generate so real images that this probability distribution should be minimized, and then overall this quantity will be minimized. And on the other hand, a discriminator will try to reduce the error by trying to correctly classifying the image real or fake. So that's basically the GAN architecture. Some examples of classic GANs are SR GANs, DC GAN, EDSR, and some examples of learning from single images are PS GAN. This is basically the GAN architecture, and other two are not basically GAN architecture, but it tries to work on single images only.
Okay, and one more thing. I think EDSR is not a GAN. It was put by mistake. It's just a method that learns from multiple images to generate
Okay.
super resolution images. So that was a mistake. Just for just to let you know. Yeah. So yeah.
Yes. So this is SinGAN, and you can see there is only one image which will be inputted to the SinGAN architecture, and from this single image only, it can generate various samples. And you can see there is quite a lot of distribution. Like it generate quite realistic example, and just learning from the one image. Uh, and here also you can see there is only one training sample, and these are all generated outputs. Say,
These are some of the applications. So the reason why we wanted to discuss the application a priori is because like it would be beneficial to like uh, when we have this application in our mind, right? So we would be like it would be easier for us to understand the architecture and what's going on beneath. So as you can see, this training image is a natural image of, let's say, hill and mountains with greenery, right? And when we go to the second row, let's say we do some kind of painting in MS Paint or draw in Linux. So the image would be something similar to like this. And the output of SinGAN would be uh, something like this. So it basically learns this probability distribution from the single image and tries to impose it into the input image that we give it to. So it's like it's really like a nice output from SinGAN's point of view. Now the second application would be editing. So let's say the training image is this. Now as you can see this, I think white borders, right? So let's say this. Okay, Shobit, can you go to this first block?
hmm,
Yeah. So let's say we want to stretch this block and we want to reduce the height of the tower. That is what our intent, right? So let's say on the second row, you can see what input that we want to give. So this input will basically tell SinGAN like, okay, so that was the training image. Now I am giving this input. So it will basically know that, okay, I have to basically stretch the first block and I have to reduce the height of the second block. So as you can see in the output row, it basically does what we wanted it to do. And it's like uh, so so anyone can ask like, why don't we go with Photoshop or something of that sort? But the thing would be like, we would cut or crop some portion of the image and then we will try to paste it at some other location, but it would be clearly visible that, yeah, some transition is going on. But here you can see this, there is a continuous flow in the image space. So that is a very good thing from SinGAN's output. Yeah. So the third application is harmonization. So harmonization is basically if you go to if you see this training image, you'll see a painting, and let's say we want to put a Christmas tree on the image. Now the output should be like we want to have the characteristic of the Christmas tree as well as we want to blend this Christmas tree with the background as well. So the in the output you can clearly see that it is happening and it's looking really good. So that's also one of the applications of SinGAN. Now, super resolution. Super resolution is like a really useful application, both from SinGAN's output as well as from Fellowship, because like when we were in the second phase, we were trying to create the data set and we were trying to augment it, right? So in that case, we had many like low resolution image for burns and like whichever classification problems that we were tackling. So at that point, super resolution could have been very handy tool because as you can see, this input image, this training image is a big image, and in that we try to mark this area that we want to super resolute. So as you can see in the output, it's like it preserves more or less this characteristic of all this windows and floor statistics, floor features. So that's a good thing. And animation is one more thing that that's possible using SinGAN, but like that's uh, that's not that really useful because like softwares are really available for that. So yeah, Shobit.
hmm. So Similar works have been done in previous years that work on single image only. There are PSGAN deep texture synthesis, and they try to overfit the training image because they are designed basically for very specific tasks like super resolution or texture expansion. However, their generation is conditional on the input image, uh, which means like they try to map image for image, while in case of SinGANs, it is purely generative and it maps noise to the image sample. Uh, these models do not generate meaningful samples when trained on non-texture images. Uh, SinGAN, on the other hand, is not restricted to texture and can handle natural images. Plus, it can perform many much tasks also. So here you can see like this is the training image, and PSGAN what it does, and like these two samples are not realistic at all. But in SinGAN, it can generate realistic looking samples. So
Okay, can you go to the previous slide?
yes.
Okay, so just to let you know, PSGAN are basically used for remote sensing purposes. So remote sensing is basically, it involves a lot of things, but in this context, I'll discuss about the satellite view images. So when a satellite takes a image of a particular area, geographic area, so one pixel may correspond to a different area, let's say a 4x4 square kilometer or 16x16 square kilometer. So the real challenge in remote sensing satellite images is like you have to like get a proper information about this specific geographic area. So let's say if if a single pixel corresponds to 16x16 square kilometers, so we would lose a lot of data because a single pixel would only contain some RGB values, right? But 16x16 square kilometer region would contain greenery, it can be a water body, it can be something else. So, or it can be a mixture of anything. So in that context, people have tried to use PSGANs to super resolute the remote sensing satellite images to come up with some useful features over this geographical area. That's why if you can see this PSGANs output, right, it is trying to extract information from the pixel. So it's basically trying to super resolute a single pixel into, let's say, a 1x1 pixel is super resoluted to 4x4 or 5x5. So it is basically trying to extract meaningful information from that. So again, it is application specific, so that is why it's not generalizing well. So that's one point that I wanted to add. Yeah.
Okay. So SinGAN uses multi-scale architecture. Like there are a large set of GANs. So on the lowest level, uh, the generator takes an noise input and tries to generate a realistic sample from it. And discriminator tries to discriminate. But the catch here is the uh, discriminator uses patch discrimination on the image, because if it will take the whole image into account, then generator will understand and it will generate the original sample only, because we have only one training image. So what we do is we use patch discrimination. There is a 11 by 11 patch uh, which is sliding over the image
Okay.
of.
Shobit,
Oh,
sorry to interrupt.
yes,
Can you use the pencil tool and
yes. Okay.
I think you can go to the effective patch size section and you can show there.
Hmm. Uh, Sorry, I forgot one thing. That in the lowest level generator, which is this one, so and here also, the image is resized to 25 by 25 pixels. It is resized, okay, and discriminator will use patch discriminator it will have overlapping patches like one we see in convolutions network. So it will like it will have input only a part of an image. So uh, from which the generator also runs the patch distribution of the image and tries to generate an a realistic image based on the patch statistics. So uh, in in this one, the image is resized to 25 by 25 pixels, and once this whole network, like this 0th level is trained, then the generated image is transferred to the upper level. Okay, now here the image is upscaled by 2x. So here it's 50 by 50 image, and we will combine it with Gaussian noise or any kind of noise for that case. And again we will do similar thing. And one more thing to note, when this whole is trained, then the weights will be transferred to the above level, so that it can continue learning from the previous, like it's like transfer learning, and it will make minor changes as it learns. So here the image
Right.
is
So it's yeah. So it's an optimization step prescribed by this authors to transfer the weights. And also one point to mention is like, as you can see, this size of this generators increase, right? So actually the architecture is constant within the generator and discriminator. The only thing is that this input to this generator and the output, right? Size of the input and output are varying. So that is basically depicted by this increasing size of G's and D's. Yeah.
yes.
Yeah. Sure. You can go on.
uh, so yes, like in all the above generator, the image is upscaled, and then again the training process is done. So if you will go to the lowest level, like here the image sizes, and one more thing to note, that the patch size is also constant in the discriminator section. Okay, so what it does is, on the lowest level, it will learn the coarse grain features, like effective patch size will be large overall in the image, and as it goes upwards, the effective patch size will be low for the image, and then the generator will learn to uh, learn fine details also. So at the lower level, generator tries to learn the coarse grain features, and as it goes higher and higher, it will learn the finer and finer details also. So that's basically the architecture.
And one more thing. Uh,
Yes.
so each level is called a scale, and you can use scale values ranging from 1 to like infinity. That's okay. But the thing is, um, let's say if you want to generate images similar to a face, right? So on a face there would be like, there are many features, let's say eyebrows, eyes, eye lenses, hair, and all those stuff, right? So effectively you will have to go up the scale, and let's say towards a bigger scale for those images having a lot of features. But let's say if you have an image of a sky in which you have clouds and just a background of a blue sky, right? So in that case you can have less number of scales and you can get a better results. So we'll go over that over the next couple of slides. So that is one point to add in this architecture. So it's not that you have to have a hierarchy of these generators and DNs. You can have a single D and a single G and D, as well as you can have multi levels of Gs depending on the context that you're working. Yeah.
Uh, so this is the generator's architecture. It uses residual connection also, like in ResNet. So it from the previous level, it takes the upscaled image and combines it with the noise, uh, and then it is passed through 5 convolutions block, and again the upscaled image is added here. So here is the reconstruction loss. So why it is useful? Because uh, a generator should also try to match similar overall statistics from the real image also. Like it's learning for patch statistics from the discriminator, and the reconstruction loss ensures that the overall image looks like similar to the original image. So that's also important. That's why this skip connection is given. So for the training, the generator uses Wallacestrian loss, which is a slightly modified version of the cross entropy loss, which we have discussed in the classic GAN section. And this is basically the reconstruction law, which we saw in the previous slide, so that the overall statistics of the image are also matched. So you can see it, training takes about 30 minutes on 1080 Ti GPU for 256 by 256 size image. Uh, and the generation at the test time is well under 1 second per image.
Okay, so go to the previous slide. So one thing to notice here is the setting is, as you can see, the setting is Z000, and this Z is basically the noise that is inserted at each scale, meaning each row. So, right. So first, the scale starts from n and it goes to 0. So it's a reverse thing, and it's interesting that only in the first G and D scale, right, they are using a noise, and in the rest of the scales they are using no noise at all. So that is one interesting thing that we found here, because like we were expecting that they are using noise everywhere, but the thing is like they are only inserting a single noise, and that is propagated to the to all the scales. And that is the reason why that we had mentioned earlier that the SinGAN basically tries to map noise to an image. So this is one of the reasons. And as you can see here, this loss is min-max loss plus this alpha times this reconstruction loss. So this reconstruction loss is basically given by this formula here. So that basically depends on the generator. So can you go to this previous slide, Shobit? So as Shobit mentioned, right? So it is important that this noise plus the input that is coming to this generator, the output should have some characteristic, uh, let's say overall characteristics similar to the input image. So that is what this reconstruction loss function is trying to do. Oh, yeah. Right, and this alpha is basically a weight parameter that you want to assign to this reconstruction loss. So in super resolution, right, you want to have, you want to really put emphasis on this, because like you will have an input image, you will have a noise, the generator would generate an output. So the output should be such that it would be a super resoluted image. So in that case, it should look similar to the real image. So in that case, this alpha should be really high, because like you will have to put a really high weight on this reconstruction loss, because it's of high importance there. Now, so depending on the context or the application that you're working, this alpha varies. But by default, they have kept 10 for all the other applications. But specifically for super resolution, they have kept alpha equals to 100. So that's one takeaway from here. Yeah. Okay, so so coming to the experiments that they have conducted, so some optimization that they have used is, as we have mentioned earlier, at each scale, meaning at each level, they have uh, like we have it's like generator is a like basically a convolutional network, so we have to have some initialization for the wave, right? So for the very first scale, they have done random initialization, but when going up the ladder, right, so they have what they've done is, once the uh, generator is base scale is trained, they have used the weights of that and propagated it to the higher level. So that is one optimization that they have done. And each scale basically trains for 2000 iteration, so each G and D has an epoch of 2000 iteration. So that is what they have given in the code base as well. In the default case, we can definitely vary it, but since they have mentioned 2000, it's better to keep that. And the optimizer that they have used is Adam here with a learning rate of 0.0005. They have decreased it by a factor of 0.1 after 1600 iterations, and the momentum parameters are 0.5 and 0.999. Now the weight of the reconstruction loss, the alpha, it is kept to 10 for all the cases. The only change is when they have tried with super resolution experiments. So their alpha would go to 100. And they have used leaky ReLU activations for the CNNs, this convolutional layers. And it has a slope of 0.2 in the negative direction on this Cartesian coordinate system. And the generator's last convolutional blocks activation is tan H instead of ReLU. They have mentioned it specifically because I think people generally try to rely on ReLU instead of tan H when they talk about generator. And discriminator's last convolution block at each scale includes, so they have not done any normalization or activation for the last convolution block of the discriminator. So this is some kind of optimization that they have done. And this is actually not mentioned in the paper. Actually, they have mentioned, they have given a link to a supplementary material in which they have mentioned all the findings that they have done during their experiments. And it is actually placed in their project's website. So you may not find this in the paper, but like in the supplementary material, you will definitely find all these things. And it's definitely a good thing to incorporate all these things while doing the experiment, because it will speed up your training, as well as the output would be really good. Yeah, next slide. Okay. Now some observations from SinGANs. It's like whenever we try to think about convolutional neural networks or convolutional layers, we definitely talk about stride, padding, and kernel size and all those things. So one observation that they have mentioned in the supplementary material is what are the effect of padding on the output of SinGAN. So let's say this training image, I don't know what is this training image, but I would call it, let's say it's a desert region and there is no water. That's why there are a lot of cracks, right? Now, let's say this boundary conditions, right? All this, Shobit, can you mark this boundary?
Yes, this.
No, the first training image, right? So this, no, not the sentence, this image, can you show the boundary cases?
Yes.
Yeah, so basically the rectangle, right, that that acts as the boundary. So how would the output be impacted if we do some kind of padding? So padding configuration highly affects the diversity between the samples at the corners. So it's like they have done three things. First, they have done layer padding. So it's like for each convolutional layer, they have done a zero padding to the input image that comes to the layer. So in all the layers, they have done zero padding. So as you can see in layer padding, this border corner areas, right, they are able to catch the distributions properly. So basically these blue regions correspond to the zero difference as if you go to the spectrum scale towards the right hand side. So blue basically denotes zero, and dark blue is the ideal case that should be reflected toward in the output. So layer padding is really beneficial, so that doesn't impact the output. But let's say we are not doing zero padding in each of the convolutional layer. We are omitting padding in the layers, but what we do is we only give padding to the input. So this is the second case, initial padding. So initial padding is basically the input. To the input you are doing zero padding. So in that case, you can see that clearly the border conditions are not that great, because like you are losing some information there. Now, again, the third case is noise padding. Noise padding is simply, it's not zero padding. It's like you give some noise, you do a padding to, and you do some kind of random, you give a random value to the padding instead of zero. So in that case, you can clearly see that the border, this corner places are really impacted, and you are not able to catch the distributions properly. Also, one more thing is like this layer padding is really helpful in the border cases, as well as if you go to the central region, it's able to catch more or less the distributions towards the center side of the image. But when you do initial padding and noise padding, these things also vary a lot. So it's better to have layer padding. So that is one observation that they have done. Yeah.
So here are the results
So
of the
can you go to the
SinGAN.
next slide?
So this first column depicts the training, only one single training image, and these are all the samples that are being generated from this image. So you can see that the overall structure is also maintained, and finer details, like in first case, there is a lot of variation in hot air balloons. Plus you can change the aspect ratio also at the inference time. So like if you will change the aspect ratio of the noise, then it will generate different aspect ratio images also. So effects of the scale. uh, Here you can see if we use n scales, so sometimes there are something weird things going on here, like you can see in zebra example. And like in if like it's and as we go up, so the finer details are modified, because it is because the lower level GAN tends to capture the coarse grain structure, so there is high variability in this, and this may cause unnatural result also. While if we start from n-1 or n-2, you can see it will create much more realistic images sample. So this is the effects of scales. Like this is the training image, and if we use only 2 scales, then this type of image is generated, which captures like textures of these images. And as we go higher in scales, it will capture textures also, plus the overall placement of objects, like this one and this one, and this moon should be at top. Like these things also can be captured as we go higher in scale. So definitely using high scales will produce much more natural looking images. So this is the real fake test that they did. So what they did, like in paired version, they showed some people uh, a real image and a fake image, and the person has to distinguish between the real and the fake. So here the confusion is 21%, almost 21.45%. And in unpaired, what they did was they showed only one image. It could be either fake or real image, and a person has to just guess whether the image is real or fake. So in that case, you can see there is high confusion, which means that the results generated from the SinGAN architecture were much more convincing, and the perfect confusion would be 50%, where the person do not know it, just he just guesses. So perfect confusion should be 50%, but you can see it's pretty high for unpaired version, and for paired it is quite high uh, for paired version also. Uh, so this is a second experiment with which they did. In the first case, they generated image from all the scales, and in the second case,
Oh, actually,
huh,
actually, basically, first scale in the sense it means like uh, when we were discussing about the architecture, right? So the lowest level scale is denoted by n. Now the next level is denoted by n-1. So n basically says that if you are using n as the basis to generate the images, the confusion would be 21.45 and 42.49. And if you go to the next level and generate the images and you give it to the users, it would be, the confusion would be even higher, because like it would produce realistic images with better quality. So that's why the confusion is increasing. Am I right, Shobit?
hmm, yes. So these are the results of super resolution. So first two cases are external methods which means they use lot of training data, and the following three are the that are based on single image only. So you can see that here the single image methods, in case of single image method, SinGAN perform much better. And also one of the case where the GAN architecture uses lot of images, SinGAN provide better results from this one. Uh, and these are PSNR and NIQE. Uh, so that's it.
So PSNR is basically a metric to see. It's like it's basically a metric used in computer, I think, digital image processing. So it's like let's say we take an example of compression. So you have an image, you compress it. So what is the quality of compressed image compared to the original image? So it is basically a ratio of that. So if the compression quality is really high, the ratio should be greater than 1. So the intuition would be in something in that direction. So as you can clearly see, the PSNR ratio for SinGAN is 26.068. So that is really good. It means that the block of the patch that we want to super resolute from the input image is really super resoluted in a very good manner. So that's a good thing. Now you can see that it is on par with ZSSR and DIP. But the thing is, like, when you come to NIQE, so NIQE is one more metric. So it's like naturalness image quality evaluator. So it's like given a model and an image, how an image is closer to the image of this model. So it's like you have an ideal model, and if you, let's say, you generate an image. So how well is that generated image closer to the natural image? So that NIQ is a metric of that. So lower NIQ basically tells that the generated image is more related to the original image. So as you can clearly see, SinGAN has 3.831. So that is a really good improvement over ZSSR and DIP. So, and it is on par with SRGAN. So the only catch is the SRGANs are trained on a lot of data. Now, training with a single image yields a significant improvement in SinGAN's point of view. So that's a really good thing. So the results are really promising. Yeah. Robert, do you want to add something?
No, it's
Yeah.
okay.
Right. So, okay, now coming to the data set. So Berkeley segmentation dataset 100 is a dataset which consists of natural scenes. It is from UC Berkeley, and they have used this dataset for this experiments. So all the images that you see here are taken from the dataset. And now super resolution results. So visually we have seen, and we have like defined two metrics on which the visual appearance and the quality are measured. Now coming to the error. So this basically external methods means this GANs are trained on a lot of data. Internal methods means these GANs are trained on a specific image. So internal method basically means that given an image, you will go inside the image and you will try to fetch internal details using patch or something similar to that sort. So that is what intuitively internal and external methods mean. So you can see this RMSE. So it's like root mean squared error. So it's SinGAN is on par with SRGAN. So that is a good thing. Now coming to NIQE, as we had mentioned earlier, it's really low. So it is basically a good statistic to. So whenever you try to deal with generative models, and especially with the images, it's better to have NIQE metric reported, because it basically shows how well your generated image is closer to the original image. So yeah, NIQ is really good for SinGAN. So SIFID. Now, before diving to SIFID, I'll talk about FID. So FID is basically freshet inception distance. So it is basically a metric that shows how you're generated. It's similar to NIQE from the context point of view, but like the formulas really differ. So it's like um, this inception network, right? People have made inception network. So this what FID does is it basically takes a layer in between. Let's say there are n layers. You take a random layer from anywhere, and you basically get the activation maps or activation function, activation values from that layer. Now, what you try to do is you will basically have a Gaussian distribution. You'll generate a data from Gaussian distribution. You will club both of this data as well as this activation values, and you will try to generate an image. Now you will have the real image, you will have this generated image. Now, how close are these two things? Is basically that is basically told by FID. Now, this FID is really helpful when you train it with a lot of data. But since our context revolves around single image, so the authors have proposed a different metric called SIFID. It's like single image, freshet, inception, distance. So it's nothing different. They basically go to the GAN. They basically take layer. I think it's they have took this last layer. They take the activation values. They similarly generate this images, and then they try to compute the distance. So the lower distance would basically tell you how like it's the lower the distance, it's like it tells you like it's having better image quality as well as diversity. So as you can see on the first scale, like on the n scale, SIFID is 0.09. As you go to the second scale, it even reduces. Now, as you go up the ladder, right, this SIFID value decreases. So it basically shows that, yeah, the image quality is improving as well as the diversity of images are also like increasing. So that's really good. Now, Shobit, will you go? Oh, go back. Go. Yeah. Now coming to the correlation. So this correlation is based on uh, we had discussed about this real and fake test, right? So in that humans were trying to decide whether it is real or fake, right? So this correlation value is based on SIFID and AMD. It's basically Amazon Mechanical Turk experiment that was termed as real or fake test. So this is the correlation on over that. So you can see here the correlation is negative. So a negative correlation means like if one value goes up, the other value should go down. So since this SIFID value goes down when you go when you increase the scales, this confusion of the users, right? Basically, this real or fake test basically tells you the confusion of the users. So when you go up the ladder, SIFID decreases, and obviously the confusion increases because the diversity and image quality are increasing, and the image quality is getting better and diversity is also getting better. So this correlation metric also shows that uh, SinGAN is like capable of producing better quality images, and the diversity is also really good. So that is what this correlation is trying to say. So in the sense, the bottom line is this: all the experiments that they have conducted, it's basically showing that going up the ladder, SinGAN is like performing really well. So yes, that's the takeaway. Next slide.
So for the super resolution, they modified the architecture a little bit. So like there are n scales, these n scales, and what super resolution is, we are trying to replicate the characteristics, and we are trying to upscale the image without reducing the characteristics or the characters of the image. So for like the architecture is based on n scales only. So if we want to super resolute the image, or uh, like uh, if we want to super resolute the image, we would need much more scales than the normal architecture would. So what they took a naive approach, And for all the above scales, they just use the last or the 0th level GAN and just use the output from this generator and input it to this generator, and this will go on and on. So when we put this type of generator one over above, the super resolution effect seems to take place. So that's why like if we reuse this GAN only above and above, we could see the super resolution effect. uh, these are the results of pin to image. Like here is the training training image, and this is the input image. And like in this section, second example, you can see that the neural style transfer and contextual transfer just generate some kind of blobs. And in SinGAN example, you can clearly see that there are some cows, uh, while in these two cases it is not very clear what these things are. So you can see that SinGAN is much better than other methods in pin to image application. uh, these are the results of image editing. Like if we move this patch here and this here, so like edited input is like this one. And this is the result of content aware move, which is used in Photoshop. And you can see the SinGANs naturally blends these patch, and it samples a convincing image which looks very similar to the training image. And these patches are not very visible in SinGAN example. And this is the harmonization effect. You can use SinGAN for harmonization also. So in the deep paint harmonization case, you can see that the starship is blended a lot more, and it is not very clearly visible. But in the SinGAN example, it is clearly visible, and it also have characteristics of the background image also. So it blends this starship image quite well. uh, and this is example you can that you can generate animations also. So here's the video.
Can you? Yeah.
uh, it is much more clear in this example.
Yeah, go to the flame. Yeah, it would be better. Okay. So, so one of the cool things about this paper is like the authors have also mentioned about the failure cases. So they have given some instruction to avoid this thing. So as I mentioned earlier, if you are dealing with face images and you want to generate faces, it's better to have a large number of scales because you want to capture very fine features from the patches, like going up the scales. So it's better to have more scales. So when they tried to generate images on the nth scale, it showed some distorted images like this. So it is definitely not useful. So when they went one scale upper, the features were coming out to be somewhat good. Then once again, when n went to n-2, the features were more prominent. So it's like it totally depends on your context. So if you are dealing with something of this thing, let's say a face image, you have to have a lot of scales. Now it totally depends on your experiment, like how many scales that you want to put. So they have not mentioned anything about optimized number of scales. But yeah, it totally depends on the experiment that we perform. So they have mentioned this failure cases as well in the supplementary material. So that is also a takeaway from that. Yeah. So these are the useful links. So this web page basically consists of all the links, including the supplementary material as well. So the paper link is here. The supplementary material is here. And the code is also available in GitHub. And one good thing is that they have coded this SinGAN in PyTorch. So if we want to build something and towards this fellowships phase 3 or something similar, you can use it. So that's a very good thing that happened. Yep. Yeah. Any questions? Hello. Hello.
Hello.
Hello?
Yes.
Yep, Mark.
So what's the input for the animations? Do you guys know by any chance?
Input for animation is a single image.
Okay, so just to make sure that I understood this
Sure,
right.
sure.
So for every time they do this, they train it on a single image. They run the single image 2,000 times through the model, and that takes
Right.
around 30 minutes. Okay, cool.
Oh, no. It's not like that. So it's like 2,000 iterations are for only a single scale. Now, depending upon number of scales that you have done, right?
Okay, so it's n times 2,000 depending on how many scales you have.
Yes. So
Okay,
actually, we don't know like we have to go to the training code and we have to see what is the default value there. I think the default value would be the value corresponding to the time that they have mentioned. Yes.
Okay, cool. Thanks.
Yeah. And one more thing, the reason why we discuss super resolution is because they have done some architectural modifications. That's why we wanted to discuss super resolution. And coming to editing, harmonization, and animation, they have not done like really major changes. So it's like you get the input from some, let's say, n scale or n-1 scale or n-2 scale, and then they have tried to do something after that. So that's like some minor things. So major modification was done to super resolution, and we want to discuss it because like it would be beneficial for this fellowship as well. So yeah. Actually, we had tried to run this code as well, but we ran out of resources on Google Colab. So probably we were I was planning to show you some super resoluted images from Burns. So I couldn't get the experiment done. Okay, guys, any other questions? Okay. Do you have any doubt from specific slide or any concept that you want to reiterate? Okay. So yeah, okay, yeah, Christian, yeah, we'll post the slides. Yeah, definitely.
Thank you, guys.
Okay. Okay. Thank you, people. Bye.
Okay.